All right. I think we're live.
Okay.
Live on YouTube. Oh, dang. It included my countdown in the go live. Like this whole YouTube stream delay stuff is wacky. Now we're live. Okay, cool.
There we go. Yep.
Hey, everybody. My name is Mark Smith, N6MTS, also known as Smitty Halibut. And with me today is Steve, KO4AFL. Not to be confused with K04AFL, like my fingers always want to type it. But Steve is here. Say hi, Steve.
How are we doing tonight, Mark?
I'm doing well. Thanks for reaching out to me. So Steve reached out to me with some questions about a circuit that he wants to design. Why don't you tell our listeners what the problem is in your life that you are trying to solve with this circuit?
So I ride motorcycles as well as do motor marshal detail for different charity bike rides. And what that consists of is me riding up and down the course, making sure all of the bicyclists are safe. The support gear vehicles are all run by hams or have hams on board. So they're constantly talking to, relaying information. And I decided to install a radio on my motorcycle, Bluetooth to my helmet, so that I could be in contact with them and tell them, hey, I've got a rider with a broken chain, whatever, at this, point on the course. I went to go ride the other day, and luckily I keep a voltmeter on the bike, and I was getting 17 volts into the battery.
That's more than 13.8 plus 15%.
Yeah. I was thinking it was more than 15%. Luckily, the radio was unplugged at the time, because if I'm not doing one of these rides, I usually keep the radio unplugged. And I'm just trying to come up with a circuit that will, basically cut the power if it's over that 13.8 plus 15%, so that I don't smoke a radio. Because luckily I just have the Vero Bluetooth controlled radio on that bike. But in the car, I'm running an ID 5100. A little bit more expensive.
A little bit more expensive, yeah.
Should I have a voltage regulator fail, and I prefer it fail to no power instead of full power, but the bike, it failed to full power, so I was lucky and didn't smoke anything.
Yeah.
Because I pay attention to my voltmeter.
Yeah. I've had power supplies, voltage regulators fail short, meaning that it ties the output directly to the input before, and thankfully I never literally let out the smoke, but I have a stack of reworked components over there that I've had to pull off of boards because, yeah. Anyway, yes, that is not an uncommon problem, unfortunately, for things. Although I have to admit, I've never seen it on a motorcycle's voltage regulator. Excuse me. Mm-hmm. So, yeah, that's an interesting problem. So you were getting 17 volts out of the alternator on the motorcycle when it was powered up.
Direct to the battery.
Yeah, that's probably not doing great things to the battery either.
Yeah, luckily, when I realized it, which I was still in the driveway, I was like, nope, parking the bike and we're taking the car.
Yeah. And you confirmed it was a dead regulator?
I did.
Yeah, okay.
I swapped the regulator, and now I'm getting the normal 13 volts. Or 14.4 when I'm running at RPM.
Yeah.
So,
you want something that will protect against over voltage. Do you also want something that will protect against under voltage?
That would be an added benefit.
Okay. So, there are a few different ways of doing this. Mark, VA3HES, in the chat room suggested one of them. So he mentions something like a crowbar circuit as protection. So let me describe what a crowbar circuit is. It is the circuit equivalent of dropping a crowbar across the positive and negative terminals of your system, which sounds bad, but what it accomplishes is that when a fault occurs, it just ties the positive and negative inputs together, which causes a surge of current. And the whole idea is that you put this crowbar on the opposite side of the fuse from your power source. So you have the battery, you have the fuse, and then you have the crowbar protection circuit.
Okay.
And so if the crowbar protection circuit sees 17 volts coming out, or 13.8 plus 15% or above, above that, then it just slams down over between positive and negative, draws a crap ton of current, and blows that fuse as quickly as possible. The advantage to this is that by crowbarring across the positive and negative sides, you are shunting that extra voltage through something other than your radio, your load, right? And so you are very unlikely to get brief high voltage or high current transients. You've already got enough of an overvoltage for it to detect that it is overvoltage, but you hopefully put your detection point well before the hardware lets out the magic smoke point, right? It's well above the something's very wrong point and well below the lets out the magic smoke point, right? And then the act of crowbarring it, all it does is it lowers the apparent voltage to the load, right? As opposed to doing a disconnect, where if you disconnect the load from that, if there's any inductance in the system, what you've done now is you have stopped current from flowing, and those inductors, like if you had a series inductor in like as a noise filter in your power line, now that current has no place to go, and that inductor will create a very high voltage. Briefly, but it will create a high voltage transient as all of that stuff dissipates. And actually, in that particular case, I think it creates a high negative voltage, if I'm thinking about it correctly, because the current wants to flow and it has to stop flowing. So to stop flowing, it ends up creating a voltage going the other direction. I may have that backwards, but the point being that those transients are a problem. And that those transients are exactly the reason why whenever you see a relay in an electronic circuit, there's always a diode, a reverse bias diode across the relay right next to the relay, because the exact same thing happens there. When you pass DC current through a relay, a magnetic field forms up, and then when you disconnect that DC voltage, it's going to create a very high negative voltage across that relay, and so the reverse bias diode just provides a place for that current to dissipate. And it only happens for a split second, but you need something to dissipate that current and keep it from creating a very high negative voltage. So anyway, that's the advantage to a crowbar circuit as opposed to something that just disconnects it. And that is definitely an option. I personally, since this is not that's great for catastrophic failures, right? Like if you've got something that's gone up to 20, 30, 40 volts, the crowbar will protect you from that. What you're talking about is not that catastrophic. And crowbars tend to be destructive. Hopefully it's only destroying, there we go, that's the verb, a fuse. But if your fuse is slow for whatever reason, then, you might find the next fusible link in your system. Anyway, the point is that it is a kind of an extreme solution to the problem. In your particular situation, I think a disconnect is still the better option, right? It's no worse than, turning off your car. Right, like when you turn off your system and it disconnects power from your radio, like that's what's happening there. So we're not really having to worry about some of those transient problems that a crowbar can help you with. So we can either build a circuit that will detect the power situation, detect under voltages and over voltages, and then disconnect a relay. Or we can use a couple of FETs or a FET, which is just a very high current passing transistor, basically. What kind of radio is it? How much power is this radio?
I believe it's like 55, 60 watts.
Okay, so we're probably looking at like 15 amp. Because like a normal 40-watt mobile rig, I think, is usually fused at 10 amps. So we would probably want to do something that can handle at least 15 or 20 amps. Okay, so that's probably going to be like a pair of MOSFETs. But that's totally doable. The advantage to the MOSFET is that the actual MOSFET itself doesn't take much current at all to control it. So just having the bike on and everything happy and providing power to the radio, the actual circuit that's doing all of that is using just a few milliamps, right? Okay. Whereas a relay is going to need 100 milliamps just for the coil to close the relay. And if you're in a power, like if the bike is on and the alternator's running, it's not going to be that big of a deal. Relays work just fine in that case. But if you ever leave the bike on, like you pull up to a roadside and you got something going on, you leave the bike on because you want the radio on, but the engine's not running. You have it on accessory, but the engine's not running. That extra 100 milliamps or so will draw down your battery faster than it would be. So I would prefer to do a FET here, but a relay would work as well. Okay. So some sort of a switch to connect and disconnect the power. Excuse me. And then the quote-unquote interesting bit is going to be the actual detection circuit. How do we detect when your voltage is above or below certain thresholds, right? And the device that we're going to use for that, and I'm going to come over here and we're going to do this. The device we're going to use for that is called a comparator. Excuse me. It's called a comparator. The LM393 is kind of the ubiquitous comparator. What a comparator is it's a device that has 3 pins on it, basically, right? 2 inputs and an output. Okay. And if the 2 inputs are labeled positive and negative, if the positive input is more positive than the negative input, then the output will be high. Okay? If the positive input is more negative than the negative input, then the output will be low. Right? So it just basically says which one of these pins has a higher voltage. If the positive pin is a higher voltage, then the output will be high. If the negative pin is a higher voltage, then the output will be low. I might have those backwards, but I'm pretty sure that's how that works.
I won't tell anybody.
So this is the data sheet of the LM393, and it looks like an op-amp. The pinouts and everything are exactly the same as an op-amp, and honestly, you can use an op-amp this way, although it saturates differently. Basically, this is an op-amp with certain characteristics that make it better to go into full saturation. Op-amps don't like being in saturation, but the comparator is designed to go into full saturation. Okay. And so the 393, what is what we have, that chip here, has 2 comparators in it. So we have an in plus for component or comparator 1 and comparator 2. So we have the positive input, the negative input for comparator 1, and then the output for comparator 1, and then positive, negative input, and output for comparator 2. And they come in various different packages and whatnot. And then lots of other data points or data things here. And then, so how do we use these comparators? Well, we could, in theory, just connect. I'm going to go back to just our faces. we could, in theory, go back, just connect your input voltage, your 13.8 volts, to one side of the comparator, but we need to bring it down some way, because there's no way, like, the comparator has to work within its working voltage. If you give it for its VCC, if it for its power supply, we probably want to give it something closer to like 5 volts. Oh no, well, the differential input voltage range equal to maximum supply voltage, which is 38 plus or minus 38 volts. Okay, so we're gonna regulate your power coming in, your battery power down to a 5 volt. So we have a clean, solid, fixed 5 volt rail, and which means that we need to work within that 5 volt range, because the comparator only knows from 5 volts to 0 volts. So if we send in a 17 volt or a 13.8 volt into one of those inputs, that's outside of its range, and it's not going to know what to do with it. So instead, we're going to drop that voltage down using a voltage divider. Do you know what a voltage divider is?
Mm-hmm.
Okay. For our audience who may not know, a voltage divider is 2 resistors on top of each other. And so if I've got an input voltage coming in here, and it goes into, let's say, a 10K resistor, and then it goes into another 10K resistor to ground, right? Those 2 10K resistors, if that's all that's there, the same amount of current has to pass through both of those resistors. So V equals IR. If you look at Ohm's law, they're the same resistance, they have the same current. That means the voltage needs to be the same across each of those resistors. My daughter is giving me a funny look. I'm on a live stream, hon. Hi. Okay. That means that the voltage across those 2 resistors needs to be the same. The top of the resistor is 5 volts. The bottom of it is ground, which means that the resistance across each of those is going to be 2.5 volts, right? And if you change the ratio of these values, that was a 10K and a 10K, then the middle is going to be half of the voltage. But let's say it's 1K and 9K. Let me do it this way. 9K on top and 1K on the bottom. Then the total is 10K, and I've only got 1K at the bottom and 9K at the top. So the top side is going to drop 9/10 of the total voltage, and the bottom part is only going to drop 1/10 of the total voltage. And so if I've got 5 volts coming in, the point between those 2 resistors is going to be half a volt, right? 0.5 volts, 1/10 of that. So you just literally by using 2 resistors, you can divide a voltage by any fraction that you want to by choosing values of those 2 resistors. So that's called a voltage divider. So what we want to do is we want to take that expected operating range of our input voltage and divide it down so that that entire range fits within 0 to 5 volts. Right. Okay. So let's set our upper limit of what we want this thing to be able to work at as 20 volts. Right. We want to be able to detect up to 20 volts. If your alternator is putting out 20 volts, something very bad is happening. So we want to bring that down. You don't want to go all the way rail to rail. So let's bring that 20 volts down to 4 volts. All right. Okay. So that means we would want a 4-to-1 ratio. So like 30K ohms and 10K ohms at the bottom. That would give us a 4-to-1 ratio because the total is 4 and the bottom part is 1. So that is a 4-to-1 ratio of voltage. So if 20 volts comes in on the top, we'll only have 4 volts coming out the bottom. But if 16 volts comes in the top, did I do that math? No, I did that math wrong. We want a 5-to-1 ratio to go from 20 volts down to 4 volts. Yes. Okay. Because 4 times 5 is 20. I can do math. Math is hard. Let's go shopping.
I try not to math on stream.
So. Yeah. So 40K on top and 10K on the bottom. That's a 5-to-1 ratio, and that'll bring 20 volts in. Will look like 4 volts down at the bottom. But if I only bring in 15 volts into the thing. That's still going to be a 5-to-1 ratio. So instead of sampling our sample point being 4 volts, our sample point will be 3 volts because it's still a 5-to-1 ratio. So the 15 volts in would look like a 3 volt at the sample point. So what we're going to do is so we've got our voltage in, and we're going to divide it by some number. And that is going to make it look like a smaller voltage at one of the inputs to the comparator. And then we're going to make another voltage divider between our fixed 5 volts, our regulated 5 volt supply and ground, that the output of that voltage is 1/5 of where we want it to detect between under voltage or over voltage and not over voltage, right? Like our set point is going to be determined by that voltage divider. So like this second voltage divider. And we can use a potentiometer so you can fine tune exactly where that set point is if you want. We'll totally do that. And so having those two inputs go into the comparator, one of them is a fixed voltage at 1/5 of your set point. The other one is the variable detected voltage that is 1/5 of the actual voltage coming in. Okay? And when the actual voltage coming in is higher than the fixed set point, then the output will go high. And that says we are over voltage. But if your variable detection input is lower than your fixed set point, then it says we are not over voltage. The output will be low. It says we are not over voltage and everything's happy. Does that make sense?
Mm-hmm.
Okay. And then we can do the exact same thing, but reversing the logic for under voltage, right? So we still do the sample, the 5-to-1 sample, and we set a different set point that's lower than the first set point, that where we want to detect if it's below this voltage, then disconnect my radio, because we don't want the radio drawing down the battery, right?
Right.
But because we want the output logic to be reversed, we will swap the inputs on the comparator. So the set point would be the positive input, and the sample would be the negative input, or vice versa. We'll figure all of that out. Now we have two outputs that when everything is happy, they're both high, right? And so we can use those and an AND gate to control our switch. If both of these are high, then our switch is connected. If either one of them drops low, then our switch is disconnected because we are either above voltage or below voltage. Does that make sense?
That does make sense.
All right, so let's throw that together really quickly in KiCAD. I'm going to go back to the screen share. All right, so we're going to make a new project in KiCAD. Power monitor. Boop-a-doo. Okay. Dang it. So, first thing we need to do is we need to drop a connector. This is going to be our power input. And then what that actual connector looks like, the physical connector, is something we'll set later. But power input. Okay, so I'm going to tie a ground to that one. And V in. Do we have a V? What do we have? We might just go with line. Right now, I'm just trying to pick an arbitrary flag to use for this to signal that this is our input voltage. Yeah, the positive input voltage that we're sampling. Like we could just go with
positive.
What's that?
You don't have a V positive in there? Or?
not just straight up positive. We do have, plus bat. Let's go with plus bat. That works.
That works.
For battery. Okay. So that is our battery input. And then we connect that to that. Okay. So that is our input connector. First, let's make the power supply for our 393s. So I'm going to do a 7805. And this is a simple voltage regulator. We need a capacitor, C pole. Value 10 microfarads. Good enough. And we'll put one on the output as well. Okay.
And the purpose of the capacitors?
So that is a thing that you kind of have to do with voltage regulators. They want large bulk capacitances on their inputs and outputs to prevent oscillations. So they are filtering, like any AC noise coming in from that will get shunted through the capacitor to ground. And so this line is more stable and consistent. And that prevents oscillations from getting into this and causing it to do all kinds of problems. It is plus 5 volts. This is a case where we know what the voltage is, and I do want to just do that. If you look at the data sheets for these things, they'll tell you how much capacitance you need on each of the inputs and outputs. 10 microfarads may not be the actual number, but it's good enough for what we're talking about here, and we can change it later if we end up deciding we need to.
Okay.
Okay, so we got our VBAT, we've got our 5 volts. Let's go draw some comparators. LM393. Unit A. So you'll notice that there are 2 units in here that with different pin numbers on each of these. And then unit C is just the power supply, the power pins. They make them separate units so that you're not having to cram it all into one space on the circuit diagram. And then we'll do that there and that there. Okay. So let me hook up the power. And then we're going to do a decoupling cap, because always do the decoupling. Value, we'll call that a 0.1 microfarad. So these analog circuits, they, again, to prevent oscillations and noise and whatnot, it's best to put a small value, actually that's relatively large, but moderate value capacitor as close to the power pins of that chip as possible. So when that chip has a sudden draw of current because something has changed, like when that changes from high to low state, that's going to draw a dramatic amount of current for a very brief period of time. And having that capacitor right next to that chip provides that a place to get that brief surge of power, and it prevents glitches and other things like that.
Okay.
So we always want to put decoupling caps next to our chips, not just analog. Digital chips need that as well. All right, so that's the power section of our comparators. Now let's drop some resistors. By the way, I am doing this assuming that you're not trying to learn KiCAD as we go and that we just want to design a system. Okay.
Yeah.
Then let's progress with that then. All right. So and we'll do another one here. I'm actually going to move those out here. Okay. So this is the voltage divider of our sample. And we said we wanted a 5-to-1 ratio of here to here. All right. So we don't want to draw any more extra current than we need to. So let's do 400K. These values are not realistic. When we actually go to build this thing, we'll have to use different values because there is no, well, in 1% you can probably get a 400K, but that's not a very common value of resistor. And then I am going to decouple this. So I'm putting another 0.1 microfarad capacitor on here, again, just to filter out any noise. It's probably not necessary, but it'll keep it from like fluctuating a lot and causing a lot of chatter on your output. Does that make sense?
It does.
Okay, so we're going to put that there and there, right? So that 400K ohm and that 100K ohm resistor is going to make this point right here be 1/5 of the voltage of VBAT. Okay? Now, technically, you would also have to include the resistance of everything tied to this node. At DC, you can ignore the capacitor, and the input to a comparator is very high, like tens of megs ohm, or high ones to tens of meg ohm, right? It's high enough that we can ignore it for this purpose. So the dominant resistances here are going to be 100K and 400K. So that's going to make that a 5-to-1 ratio voltage drop here. Okay, so that's our sample. We also need to make a set point. And let's do this with a potentiometer. All right. And we'll make that 100K. And again, it doesn't matter too much what this voltage is or what the value is here, because what we're interested in is the ratio between what's on the top side and what's on the bottom side. Actually, I make that mistake all the damn time, so I'm going to flip that over. And we'll take our ground and our 5 volts, because we want this one to be fixed voltage. We do not want this voltage to vary with VBAT. Okay. Right? As VBAT goes up and down, the reason we have this voltage regulator here is that 5 volts is consistent. As long as VBAT is at least 2 volts above 5 volts, so as long as this is at least 7 volts, then our 5 volts will be solid and consistent. And then when we put a voltage divider on that 5 volts, it will be solid and consistent as well, right? Okay.
And if my mobile battery gets down to 7 volts, I have bigger issues.
You've got bigger issues, exactly right. So this, as we have it drawn, is the comparator. This is the heart of the system that we're building, okay? So we are taking our input voltage, we're cutting it down by 1/5, 1/5, a 5-to-1 ratio, and we are sending that to one input of our comparator. We are taking a fixed 5 volts, and then we set a set point using this potentiometer to be 1/5 of our over voltage point.
Okay.
Right? And we set that into the other input of the comparator. And then actually, I think we want these active low. Wait a minute. The 393, is the 393 open collector? Next generation of the industry in the 393. These next generation versions comparators feature lower offset voltage, high supply voltage, lower supply current. Two independent voltage comparators that are designed to operate from a single power supply over a wide range of current is independent. Okay, hold on. Common mode input voltage ranges includes ground. Differential input voltage range includes a maximum 38. Low output saturation voltage. Okay. So output put in comparator 1. Output voltage. Okay. Recommended, nope. Thermal. ESD ratings, electrical characteristics. Input offset voltage, input current, common mode range. Low level output voltage. So when it detects a low, it is saying that the output pin will be 110 millivolts or less, typically. And it will never be more than 400 millivolts. So a low output is never going to be worse than 0.4 volts. And that's assuming that you're only sinking 4 milliamps from it. Swing from V minus. Yeah, okay. High level output leakage current. Output current. Low level output current. So it can sink from at least 6 and typically up to 21 milliamps. Okay. But what is the high? So I think this is open collector. 393B. So it's not saying what the output high voltage is. And I think the reason for that is that output high just means high impedance. So it doesn't actually drive it high. All it does is it drives it low. And I'll explain that in a second as soon as I can find the equivalent circuit inside. Are they going to include an equivalent circuit? Yes, they are. Okay, yep, that is exactly what that is. Okay, so open collector. What does open collector mean? Open collector means that the output here is just connected to the collector of the transistor. Like this is all detection circuit over here, right? The real business end of the output is this transistor right here. So this is connected to the gate of the transistor, and that's either going to turn this transistor on or off. And so when that transistor is turned on, then the output will be actively pulled low to ground. Okay? So whatever voltage or current source you have over here will be able to dump some current through this to ground. And, if you've got a resistor over here up to plus 5 volts, that will pull some current through that resistor, and then whatever your saturation voltage of that BJT is, looked like 0.4 volts or 0.1 volts, is what you'll see on the output. But when this is turned off, there's nothing else on this pin to cause it to go anywhere. When you turn off a transistor, it doesn't automatically go high, right? There's nothing pulling this output up to VCC, right? So at that, when this base gets turned off, what happens to this transistor is that it looks like a high impedance, megohm, 10 megohm, something like that. No current can flow through here. So unless you have something else pulling it high, it won't do anything. It'll just sit there. The advantage to open collector is that I can put multiples of these in parallel. So I can have multiple outputs all connected in parallel. And if one of them, and then I have one external pull-up resistor to VCC, right?
Okay.
And so now, if none of the output transistors are turned on, then the output pin, no current is flowing, and that output pin gets pulled up to VCC. And it looks like a 5 volts. because there's no current flowing through that resistor. So there's 0 voltage drop across it, so it looks like a 5 volts. But as soon as one of those transistors gets turned on, it will draw the current through that resistor and pull it to ground, and that will bring the output down to ground. If I happen to have 2 of those, they're both pulling current through the resistor. The resistor isn't going to pass any more current. It's just going to split the load across the 2 different transistors. It's still ground, right? So by putting both of those in parallel and calling ground your active state, we can put 2 of these in parallel and call it an OR gate at that point, right?
Okay.
Because one of them, if either one of them are active, it will pull the output to 0. Both of them have to not be active for the output to go high, right? Does that make sense?
Okay. Mm-hmm.
It's kind of like if you have 2 switches in parallel, right? Pushing either switch will let current pass through that path. And if you push both switches, current still passes, but it's not really any different than if you have just one of the buttons pressed, right? But if you have neither of them pressed, then there's no path for the current to go through. That's what we're doing with that open collector. Okay, that's what I needed to know. So the 393 is an open collector output, which means that I can build another one of these. Actually,
Copy pasta.
Copy pasta. Okay, except, so this if this is going to be over voltage, the other one's going to be under voltage detection. Now I actually have to think about the logic. Okay, so if the battery voltage is higher than our set point, so that's the over voltage protection, then that's going to make this active, which is going to pull this down to ground.
Mm-hmm.
So that's correct. But for under voltage, we need to detect if the battery voltage is below our set point. So we actually want to flip this. Nope, not that way. That way. There we go. So does that make sense?
It does.
Okay. So we need to reverse our input pins, and rather than reversing these circuits, which I could do, I just flip this over. But now, if either of these conditions are met, that is to say that VBAT is higher than that set point, than our over voltage set point, or if VBAT is below the under voltage set point, then that node will go high. So let me pull that up, except that I probably want that to be 10K. And I want to pull that up to 5 volts. Okay, so now add a net label. Yeah. Power good. Or do I want to do, hang on, power fault. So, nope, it's not tilde. What is it? Shoot. Dang it. Okay. No, it's just a label. That's right. It's this that would do it. Power fault. Apparently it's not tilde. What the heck is it? There's a character I can put here that will make it have a bar over it, which means active low. Shoot.
Yeah, I'm not into KiCAD yet, so.
I don't remember what it is. Let's ask the Googles. That one. KiCAD active low label. To place a line above the pin text, add curly brackets around the name and prefix with the tilde. What? I don't remember that. Hell. All right.
Okay.
So active low power fault is what this is telling us. So active high power good. Now, which of those indicators you use is kind of, 6 of one, half dozen of the other. But yeah. Okay. So there's our detection. Now we want to pass current. MOSFET. I don't know. There are probably better MOSFETs for this. Okay, let's do this. IRF 510. That's the one MOSFET I know. How much current can you pass? Oh, no. I do not want a N channel. I want a P channel. N channels are great at switching loads that are to ground, like disconnecting a load from ground, but they're not so good at disconnecting a load from power. And you don't want your radio disconnected from ground because the radio has lots of other paths to ground, like your coax shield. If your antenna is well connected to your motorcycle body, you might get power passing through that. So you definitely do not want low side switching. So we don't want to use N channel MOSFETs. We want to use P channel MOSFETs. Okay. P channel MOSFET. Shoot. I'm not nearly as familiar with P-channel MOSFET numbers. Typical P-channel MOSFET. The IRF 9540 is the most common P-channel MOSFET. Great. Okay. There we are. VDS. RDS on is 0.2 ohms. So the way a MOSFET works is that it looks like a variable resistance controlled by the voltage at the gate. So the kind of the how good is the thing is determined by the resistance between the drain and the source when it's on, which is what RDS on means. And it's measured in ohms. So how low is the resistance between the drain and the source when this thing is turned all the way on? And the answer here is apparently 0.2 ohms. If your gate and source voltage is minus 10, so there's 10 volts between, here. If your gate is at least 10 volts lower than your source, then, which is the full saturation, then this will be 0.2 volts. And then if the gate to source voltage is 0, then it's completely shut off. So, but what I want is drain source voltage, gate source voltage. I want to know with a continuous drain current. That's what I'm looking for. Okay. ID. When the thing is at 100 degrees C, it can pull 13 amps. When it's at 25 C, it can pull 19 amps. All right. I think that's good. That should be good for your radio because you're likely never to get above 50 or 60 C, so it'll be somewhere between 19 and 13. Right? Like pulled from my ass. There might be a temperature graph in here somewhere. Drain current, junction temperature. So we'll call it 60 C, which is like a really bad day. RDS on, that's going to be RDS of 1.25. Do you have a junction temperature versus current? Drain to source voltage, drain current, capacitance. Nope. Case temperature. There it is. Case temperature to drain current. So we'll call right about here. Yeah, drain current is still more than 16 amps. All right, so one of these should do your radio just fine.
Okay.
Okay. You in the chat room. Yes, you. Ask us questions. Say hi. Do whatever you're going to do. Oh, shoot. I need that part number. What was it? IRF 9540. IRF 9540. Look at that. So it says 23 amps. Yeah, that's all like best case scenario. All right. And I like looking at those like that. So we're going to take VBAT. The input is from the battery, and we're going to call, we have to drop a new voltage output here. Bah. VDC. Why not? Yikes. That's big. Not what I wanted. There's probably a way to create my own of these, but I have never figured it out. VSW. V-switched. Yay.
Okay.
All right. I dubbed the V-switched. Okay. So now our drain, no, that's the source. That's the drain. There we go. The thingy is pointing to the source. So the thingy is pointing to the source. So that's where our source. So we need to have this pulled down to ground when we want to turn this on, because then your gate, your drain to gate voltage, actually I think it's source to drain is the one, or source to gate is the one that matters, is going to be minus whatever your battery voltage is. And that's what's going to slam this thing into turning it on. Okay?
Okay.
But when we want this to be off, then we need this to be pulled up to the input voltage. You know what? We actually want that. So we are going to use that. The fact that this is open collector is going to come in handy here, because we actually don't want the 393 to drive our high. We want the high to be to be driven by the battery, because we want this MOSFET to, when neither of these are active, right? When neither of them are active, then it is shit. No, this is backwards. When neither of these are active, it's going to be pulled up, and that would turn that off right there. Okay, so I need another one. Logic is backwards. 2N7000. Let's put this one in here. Okay, we're going to do a simple NOT gate here. And this also protects the 393 from being overvolted by that pull-up. Okay. No, we're good. We're good. We're good. We're all fine here. How are you? Nope, nope, nope. That one. So we're putting that 10K back to where it is. All right. So when we are in the good state, neither over voltage nor under voltage, both of these are turned off. So they are both in the high impedance state. So that pull up to 5 volts is going to pull that up, which is going to turn this transistor on. Which is going to make its output tied to ground. Yep, here we are. Okay, I think that's the circuit right there. So when everything's happy, we are in range. Both of these are off. Both of these are high impedance, which means this is going to be dominant. That's going to go up to 5 volts. That 5 volts is going to turn this MOSFET on, which is going to pull. This is a N-channel MOSFET, which is going to pull this down to ground. And that pulling this line down to ground is going to activate this MOSFET, which will allow the battery to pass to V-switch.
Okay.
Okay? Because that's going to be a much lower resistance than this will be. This will be like half an ohm, and that's 10K ohms. So that half an ohm is going to dominate, and your gate here is going to get pulled down to ground. And that's going to turn on your P-channel MOSFET and let power go through. However, as soon as either of these go into fault, then either one of these will be pulled to ground. And that's going to pull a little bit of current through there, but more importantly, it's going to pull that gate to ground, which is going to turn this transistor off. This transistor will be off, which means that this gate will be pulled up to VBAT. And that will turn this gate off. That'll turn off this transistor as well, which means VSW will get disconnected.
Okay.
Okay. So that's it. That's the heart of the battery voltage thingy thing. Okay. I say something and now everybody in the chat room starts talking.
I'll go watch and chat. So
yep, there we go. Did you think about using 2 LM431 shunt regulators to do the high-low detection? No, I don't know what an LM431 is. Let's take a look at that, because I honestly don't know what that is. 431. Adjustable precision Zener shunt regulator. Cathode anode. This is a 3-terminal adjustable shunt regulator with ensured temperature stability over the entire temperature range. The output voltage may be set at any level greater than 2.5 volts up to 36 volts merely by selecting 2 external resistors that act as a voltage divider network. Okay, so which is basically what we're doing. Due to the sharp turn-on characteristics, this device is excellent replacement for many Zener diode applications. Okay, so this sounds like it is a voltage reference, which would replace this part here. It's more precision. Jack is saying jump to page 17 for an example. First off, let me make this big so people on the stream can see it. And then 17. No, there you go. Over voltage and under voltage protection circuit.
Already done.
There you go. So, to answer your question, Jack, no, I had not considered doing this. But there, as with so many things in life, there are many different ways of skinning a cat. And don't let my cats hear me say that, because I don't want to skin them. But that's another option, right? Like that circuit right there will do something very similar. Okay, let's keep reading down here. Ham Radio agree. Oh, no, that's Steve. It's far less elegant solution to what Mark is coming up with. Scale his circuit up, and it would make for a great protection circuit for a power pole distribution block. True. Because it won't blow up any fuses or risk blowing up anything else. You know what's going on here?
That's Joe giving me a hard time.
Yep. To have the power connectors be power poles, so it would be past the power and everything was good. Yep, that's exactly what I plan on doing. That is why I asked Mark. 50K ways to do anything, and none of them are the correct way. That's right. They're all correct in some way and incorrect in others. So, yeah, that is the heart of the system. Now, okay, let's stop here. Are there any questions from you, Steve? Because I've been doing an awful lot of blabby blab, and you've been sitting there going, Are there any questions from you on this circuit? What it does, how it works, why I did it this way, or anything like that?
I'm assuming you did it this way because this is what you know.
Yep, exactly that.
How it works, the way you've been talking makes sense to me. I kind of got it from our email, but I wasn't 100%, which is why I wanted to come on stream and, actually see it done in KiCAD.
Yep.
The potentiometer or variable resistor, basically, would set our reference voltage for the 393?
Correct.
Okay. So, yeah, about the only other thing I might add to it would be a LED to indicate which way it faulted. But,
yeah. That, if you want to know whether it was under or over, the unfortunate thing is here that we're using both of those, like the two outputs are tied together the way it is right now. So we would have to split them into two different things and then put an LED on each one. And then I'd have to think about whether, anding this or oring this. Like now you would have two N7000s, and I would have to think about whether they would be stacked on top of each other or whether they would be parallel with each other. Yeah. We could do that. It's going to add some complexity that isn't the basis of what we're trying to do. Actually, we could do it with a couple of diodes. All right, I lied. We're going to do it. Challenge accepted. So the way we're going to do this is, let's see here. Okay. First thing we're going to do is value 1K. And then we're going to drop an LED. And then give me my 5 volt. Okay. Copy pasta. Okay. So as is, yeah, Jack thought of the same way I did of putting a couple of diodes in here to mix these together. So as it is right now, again, when this is not active, when it is within the happy state, then this is not active, and this is a high impedance, and there's no way for current to flow through there, so the LED is not lit. As soon as you go into overvoltage detection, pin 1 gets tied to ground, which allows current to flow from 5 volts through the LED, through the 1K into ground. And so that'll turn on that LED. And then same thing with the undervoltage over here. Now the question is, how do I get either of these to turn this guy on, or turn this guy off, I guess, without them also turning on the other LED. And so the way we're going to do this is with a couple of diodes. Yes. 1 and 41, 48, whatever. All right. So what does that do? Well, let's look at the case where neither of these are active. The LEDs are not turned on. Neither of these are pulling current through here. So the 5 volts pulls this up. This is turned on. Everything is the same as it was before, right? But as soon as one of these turns on, so let's say this one is turned on, so this node here is pulled down to ground. Well, the good news is that allows current to flow through here, so the LED turns on. This is now ground, which means this here, any current will flow from 5 volts through that 10K, through that diode to ground. Okay? But this one is not grounded. This is still high impedance. So no current will flow from the 5 volts through that 10K through that diode to ground, right? And pulling this one to ground here does not allow current to flow back this direction because that diode will stop it from flowing that direction. Did that make sense?
Yep.
Okay. So by putting those two diodes here, we can have each of these LEDs turn on when their respective 393 turns on without turning on the other one. And we needed those diodes to prevent, like if I didn't have this diode, if this were just connected like that, then when this one turned on, current could flow from 5 volts through that LED, through that resistor, up through this wire, through that diode to ground. Right? And we don't want that.
So you get both LEDs turning on.
Yeah, because then you get both LEDs turning on and you can't tell whether it's an under or an over voltage. Right? So by putting both of those diodes in there, we now can keep those detection circuits separate, but either one of them can pull this to ground and turn this off, which will let this gate go up to VBAT and turn that off. That make sense?
It does.
Okay. So now we've got our detection LEDs. We can now tell when we're in an undervolt or an overvolt situation. Cool. Anything else?
No, that's because the power input's going to give you your VBAT, and then the voltage regulator is going to knock you down to your 5 volt. So you'll have your BAT rail, your 5 volt rail, and your ground. And then your V switch would go out to power poles.
Yep. I'm just realizing that I forgot to put the output connector on here. There we go. That's it. All right. Now, here's the awkward part. Let me go ahead and save that. Here's the awkward part. A friend of mine pointed me to this neat little chip right here. The LTC 4365. Over voltage, under voltage, and reverse supply protection controller. It does exactly the same thing that we were just doing. So it's a single chip that you can give. You do the voltage divider dance, but it has a single voltage divide. You make it so that your over voltage and your reference points here are 0.5 volts. So we said we're going to do a fixed division of our input voltage, and then we'll set our reference voltage to whatever we want the reference. We'll set our comparator input reference voltage to 1/5 of the actual voltage we're trying to detect. Right. Here they went the other way, and they say the reference voltage is fixed at 0.5 volts. You adjust the voltage dividers of your sample so that your sampled voltage is 0.5 volts at either over voltage or under voltage to detect when it goes in. So it's changing which one is variable.
Okay.
Right? And then it also has another control for a shutdown. So these are comparators, and then shutdown is just an active low. So if the shutdown pin is high, then everything gets turned on. You can also have the shutdown, pull it down to ground, and then it just turns off the load at command, as opposed to an under voltage or over voltage situation. And then it's using a series FET here, although it's doing it differently than we did. And then there's your output. And then it also has a fault output detection. So we were able to keep it as two separate faults, so we knew whether it was under or over voltage. This one combines it into a single output. You can't tell whether it's under or over, but it will tell you that there is a fault. Okay. So let's go look at the innards of this thing, because they usually give you kind of equivalent circuits, or at least logically. Hey, look, it's a couple of comparators. And some AND logic, or logic in this case. And then that OR logic ends up controlling a MOSFET. Or in this case, that's just the fault indicator.
Right.
But it controls some logic over here, and then that controls a MOSFET to actually switch the power. So basically, they did the exact same thing that we did. Right. So
as Mark says, and someone already built a better mousetrap in one chip.
Exactly right. Yep. And this mousetrap also includes a bunch of hysteresis. Right. Ours did not have any hysteresis. Hysteresis meaning that once it's the detection point is 0.5 volts. Once your over voltage detection goes above 0.5 volts, then your over detection says, "Crap, we're bad. Let's disconnect the load." But if it drops down to 0.499 volts and then goes back up to 501 and then down below 4.99 and back up to 5.1 or 0.501, it's not going to sit there and switch on and off a whole bunch. Once it goes above 0.5, it has to go below 0.475. So it's got 25 millivolts of hysteresis. So it has to go below 0.475 before it will turn back on again. And then it has to go above 0.5 volts to turn off again, and then below 4.75 to turn on again. So if you've got a signal that is right close to the transition period or the transition voltage and a little bit noisy, it's not going to just keep turning off and on and off and on and off and on and off and on. It actually has to recover a fair bit before it will actually turn it back on again. That's called hysteresis. And both of these comparators have 25 millivolts of hysteresis. Ours do not. If our in the design that we did, where is it? There it is, KiCAD. In this design, if the VBAT comes in and is oscillating just above and below our reference voltage set by this potentiometer here, this thing's going to chatter. It's going to turn off and on and off and on and off and on and off and on, and that's probably not what you want. So having a little bit of hysteresis here is a good idea. We tried to deal with that by throwing a filter cap on here. And what that does is that prevents a lot of the high-frequency noise from getting here. That'll just shunt high-frequency noise down to ground. And you can put a much bigger capacitor here, and that will cause the entire thing to move much slower. But it will still, if it's still oscillating even slowly above and below the threshold voltage, it'll chatter a lot. So hysteresis is good. And then the rest of this is just all kind of support circuitry to do things like gate pull down. So that's constant current for pulling down the gate. There's the shutdown input pin, gate charge pump. Oh, because the you need to get your gate voltage very close to the input voltage, or even a little bit above the input voltage to really shut down that MOSFET. So that charge pump there is there to make sure that the gate control will absolutely positively shut off that MOSFET. So yeah, this is a chip that does all the things that we were just talking about. You still have an external MOSFET for it to actually switch the load. And then you have this chip, and you've got 3 resistors that you have to choose the values of these 3 resistors very carefully to set your over voltage and under voltage limits. And you can put potentiometers in here to provide some fine control from that. But you have to do some math ahead of time in the design phase to get the right values here. And then shutdown is just pulled up to VIN. And that's it. It's a tiny little 8-pin package. So I learned about this about 30 minutes before turning the stream on. But I decided it was still educational to go through this whole process.
Oh, absolutely.
Right? Like, to understand what's going on here and why this is doing what it's doing and how it does it and all that fun stuff. Because this chip is doing the same thing. Right? The exact same comparators, except they have hysteresis. And you'll notice even that the inputs are swapped, right? Under voltage is the reference is on plus and the sample is on minus. Over voltage, the reference is on minus and the sample is on plus, right? So they even have the reversed comparator, just like we did. And they're using an OR gate here, but we did it with a couple of diodes, right? If either one of these is pulled to ground, then the output would be pulled to ground. But if neither of them are pulled to ground, then the output will be allowed to be pulled high. So I guess technically...
And they're doing that on a 12-volt supply, looks like.
12 volts is the VBAT in our case.
Right.
Right? So wide operating range from 2.5 volts to 34 volts. Right? So you can operate this on any wild range of voltages. And it won't actually fail until minus 40 volts and plus 60 volts. It can withstand those voltages, but it likes to operate in this range.
Holy cow. Okay.
So, neat little chip. Thank you to Bill for telling me about this. Bill is a ham. What is he? AB6BW, I think. He's a friend and former coworker of mine, but more a friend. He was a friend before he was a coworker. Anyway, he gets credit for helping me and convincing me to design my first circuit board. This is back in college. Actually, to put a radio on a motorcycle. It wasn't a power protection. It was a audio interface board for interfacing my D700, my Kenwood D700, into the audio in my helmet. I wanted a PTT button on the handlebars, and the microphone and headphone audio in my helmet. But I still wanted to be able to have the hand mic available in the trunk box, so that I could just pick up the hand mic and use that if I wanted to. And then the board also had a power supply for a GPS module. This was more than 20 years ago, about 20 years ago. And so GPSs were not nearly as common and cheap as they are now. There was a $20 GPS floating around various different flea markets that was a fine GPS, but it output a proprietary binary data format. It was not NEMA, and there was no way to make it NEMA. So Bion, from Bionics, the guy who makes the tiny trackers, one of his earliest products was a little 8-pin PIC microcontroller that would translate this binary GPS output format into NMEA data. And so I bought one of those chips and a Max 232. So the data coming out of the GPS was TTL data. It went through this translator chip. It was still TTL, but the D700 needed RS-232 levels, so the Max 232 converted it to RS-232, and all the power supply for all of that, the power supply for the GPS itself, and a battery for the GPS to remember its data, and then the outputs to the radio, and then also all of this audio stuff. So if I picked up the hand mic and pressed PTT on that, its audio would go through. When I hit PTT on the handlebars, the audio from the headset would go through. And then, of course, the speaker audio got sent up here as well. So all of that was on one little circuit board, like 2.5 by 3.8 inches. And Bill was the one who helped me design that because he ran his own electronics company at the time. We were living together, and we did some very cool stuff. I credit Bill for a lot of my electronics know-how and whatnot these days.
I think you've mentioned him on the workbench before.
Excuse me, I probably have. Excuse me. Oh, wow. I just nailed a glob of spit. Anyway, the point being that I posted a link to this video stream on my BBS, which he's a member of. And he's all, oh, have you looked at this chip? And he pointed me to this chip, and I finally had a chance to look at it this afternoon. If anything, tonight was a good crash course in KiCAD. I have better crash courses in KiCAD, actually, because I did not, I intentionally did not go through this is how you do this in KiCAD. We kind of I just blew through and used KiCAD without actually explaining how to use it. If you want a crash course in KiCAD, go look at the streams I did with Paul Brown, or Braun, not sure how you pronounce his last name, WD9GCO, WB9GCO? I don't remember his call sign because I'm horrible with call signs. He's Paul from Amateur Radio Newsline. He and I did some live streams where he was designing his own open headset interconnect standard interface. Okay. And I was helping him out with that and walking him through KiCAD on that as well. So, okie dokie. Steve, we are... Actually, no, we're about where I expected us to be, about an hour and a half in, so that's not too bad. Any other questions, or what do you want to do from here?
Well, I think I'm probably going to look at that chip and see what I need to do to put it on a circuit board with power poles.
Okay.
Just to make it easy. And I'm kind of curious if it'll take maybe even possibly an HF radio, like an 857.
You would need more power handling here. So the RF 9540 was good for, we were looking at 16 amps, I think, in the configuration that we were expecting to use it on. You could put two of those in parallel, and that should give you about 30 amps, which would be enough for an HF rig. I say this with a lot of question marks because I've never actually done that. I've seen circuits that do that. I don't know if there's any magic that needs to be taken care of when parallelizing MOSFETs. Although if you're at a point where you're operating an HF rig, you're going to be drawing enough power that the 100 milliamps of a relay may not be that big of a deal. So you may be at the point there where you want to just supply the current through a relay that can handle the amount of current that you want and just be done with it.
I was just thinking, if this was reproducible on a circuit board form, I could have one, for each of my vehicles should voltage regulators go bad in alternators or whatever.
Yep.
So if I've got, like in my truck where I've got the 857, I could run it through that. Or in my car, I'm just running like the 5100 or the 4100, depending on which vehicle. Yeah. A lot less power there.
So the 857, is that a full 100 watts?
It is.
Okay. Yeah, then
it's
you want
the all band, all mode in the 891 size.
Okay. Then you probably want to make sure that it's good for at least 25 amps, I think. I think 25 amps is a typical fuse size on those.
Okay.
Yeah, so the goal is to make sure that your MOSFETs are not your fuse, right? And similarly, when you lay out the circuit board on these, you need to make sure that those are some damn thick traces. And maybe even expose some copper on the top and make it so that you can solder on some solid core copper wire, strip the wire and just solder it directly onto the board just to make a big fat copper path between the two. It's all doable.
Or I could use the circuit board to trigger a relay for the HF rig.
Yep, that too. Exactly that as well.
Because I know I could get a 30 amp relay in a 5-pin design that's real easy to wire up.
I've got a box of them over there for some projects that never happened.
Not a sore subject, is it?
No. It's just priorities shifted, and I needed to go. I needed to stop squirreling around and working on a bunch of different things, and I decided to work on. Let's see here. I was working on SOAR at the time, and I decided to stop squirreling around and concentrated on SOAR. And then once SOAR failed or ran into issues, I went over to the OHIS side of things. Bill Mungavin, I am really sorry for butchering your name, Bill. He asked the question that I think we probably answered just a few seconds after he typed it because of the YouTube delay. Could you use the output to drive a relay instead of pushing the entire load through a MOSFET? Yes, exactly that. And I think we were saying that as like just a few seconds before you typed the question in. And I think because of the YouTube delay, you hadn't heard that yet. That was really educational. Thank you, Mark. Well, thank you, Bill. I appreciate you being here. If there are any other questions or anything else in the chat room, please hit us up. While we're waiting for those, do you want to tell the audience how much you love your contesting console?
I was going to see if we could roll into that OHIS. So yeah, I have used the contest console on a couple of different outings now where I've deployed the club's radio trailer, and I've had a logger and an operator at one station, and we can control the volume and still have that intercom in between, so you don't not constantly lifting the headset off. What'd you say? Exactly. But yeah, the contest console is money, and the fact that we have two different radios, we have a Yaesu and a ICOM radio, and I could just buy the same headset, for all four stations and not have to worry about it. It's golden. The only issue we have run into so far is the AC unit in the trailer gives off a lot of white noise, but it's a ductless unit because it's a typical RV unit, and there's no real way to silence it.
When you say noise, you mean audio noise, or do you mean RF noise?
Audio noise.
Okay. Like picked up through the microphones?
picked up through the microphones.
Okay. What kind of headset are you using?
We've got the Synagers. They're like $20 gaming headsets.
Okay.
So CTIA standard.
Do they claim to have noise canceling microphones?
You would ask me that.
I would.
Let me jump over to the Amazon and look at my order.
Because I know some headsets do use noise canceling microphone elements where you've got two microphone elements pointing in opposite directions. One of them points directly at your mouth and one of them points away from your mouth. And then the microphone elements are connected out of phase. So anything that both microphone elements hear gets canceled. And it's great for like white noise background kind of noise. But then anything that is different between the two elements gets received. And so since one of them is pointed directly at your mouth and one of them is pointed directly away from your mouth, one of them is going to hear your speech a lot more than the other one will.
It does say it has a noise canceling microphone.
Okay. Interesting. Then I don't know. And
course,
you could.
I do have guys that are wanting to use aviation headsets, and I'm like, yeah, find me the 3/16 jack to build my own OHIS and
Search for PJ-068.
Uh-huh.
They exist. You can get them on eBay. Come on. Okay.
And that's a carbon equivalent element
Well,
in those, I believe.
yes, but specifically the connector is irrelevant. But yeah,
Right.
You may run into issues with the microphone levels. Seriously, that does not look like a PJ-068.
So that is the PJ-068.
That looks like a quarter-inch, but
plug side.
There we go.
Yeah, there we go. That's the one we need.
That's the part you need.
Yep.
Yeah. And so old school aviation headsets will probably not work. Anything that has a real carbon microphone element, well, shoot, it might actually, because the lower voltage is going to give it a lower signal output, but the signal output is so hot on those things anyway, the lower signal output may actually work out just about right. But modern aviation headsets, I don't think are using literal carbon elements. I think they are using electret mic elements and then amplifying those.
Mm-hmm.
And so if you give it the 5 volts that an electret mic element needs, it may still work. Now, I don't know what the output level is going to be. The User Pro does have a trim pot, so you can bring down hot mics to be in range. But I don't know for sure that a 5 volts is going to be enough to drive a modern aviation headset. Yeah, James, KI5OEB, says modern ones are electret. Yes, I agree with that. The question is whether modern aviation headsets are designed to be driven by somewhere between like 8 and 36 volts of bias voltage on the mic line. Whether the modern aviation headset will work with only 5 volts on the mic line, or whether it's doing some sort of a voltage drop that 5 volts gets to be too low to actually drive the electret. I don't know the answer to that question. So what I'm really looking for is someone with an aviation headset to rig up some adapters and try this out. And tell me how this works. I've been exchanging emails with someone from from my groups.io list who was asking me how to do exactly that, but I don't know how quickly they're going to be able to do that or not. Old military headset is not compatible. Do you mean that from the fact that they are actual carbon mic elements? Because that I am pretty sure that will not work. I was not aware of the specs.
Well, and that's the other thing is the specs are so hard to find
For aviation headsets?
for the aviation headsets.
Yeah.
But they should be pretty much standard if you're looking general aviation headsets.
So I have found general aviation headset specification sheets. The problem is that they specify what general aviation is. They don't specify what they will actually work with.
Right.
Right? Like if you plug a general aviation headset microphone into something that's expecting to drive an electorate, you're definitely out of spec. Right? The right thing to do is to boost up the 5 volts that OHIS has and turn that into a proper bias voltage for the carbon equivalent microphone. And then pad down the audio so that you're not overdriving the OHIS standard. That's the correct thing to do. Until I or somebody else makes an aviation headset specific user pro or user adapter, the question is, will just connecting it to something expecting an electric microphone work? And I don't know the answer to that question. I don't have an aviation headset to test that with.
Yeah, I was going to say, I may have to pick up some of those plugs and just do a step down from that to, the 3.5 millimeter.
Yep.
And plug it in and try it.
If you do, please let me know what the results are.
Pray I don't fry my $600 headset.
You are very unlikely to fry the headset because you are going to be undervolting the headset, not overvolting it. If anything, it's just going to not work. Says the guy who will absolutely not back that up with any sort of a financial guarantee.
Right. Well, considering I haven't used that headset since 2006.
Yeah, James is offering to send me a couple of headsets. Honestly, James, what I'm looking for is somebody else who wants to do this testing for me. I don't have the time or the energy right now to do this exact testing. I think I'm going to pass, James. Thank you very much. James is, again, offering to send me a Lightspeed and a military headset. I'm going to instead turn this around and say, if you want to help out, you want to make some adapters, although it sounds like Steve might be doing that as well.
Yep. I'm going to grab my Flightcom and I'm going to order those adapters, and because that should work under the CTIA standard, right?
I would, if you've already got a CTIA User Pro, yes, but I would recommend that if you're going to do it, that you either modify your CTIA or go with something like a Radio Sport or the Heil Electret. Specifically, you want to keep your headphone ground and your microphone ground separate if you can.
Okay.
The CTIA necessarily has to tie them together because it's only got 4 pins for left audio, right audio, microphone, and ground. And so the ground is shared between mic ground and headphone ground. But in the aviation headset, I'm pretty sure they're kept separate, and it is a far better thing to keep them separate if you can. So
okay, I may shoot you some money and have you send me a Heil electric one or the Radio Sport configuration.
Yeah,
whichever you think is better.
If anything, I'll send you a Radio Sport because so far 0 of those have sold. Apparently, that is not nearly as popular as I was expecting them to be. But yeah, we'll work that offline.
Yeah.
So
because I know I have another contest console coming my way. So
yes, that's right. So the contest console that Steve has is a prototype unit that I sent him as just kind of a, like, please make sure and tell me that I'm not just smoking crack, because I think it's totally awesome. But I'm also the designer of the thing, so obviously I think it's awesome. I wanted another person to verify that, yes, this really is as cool as I think it is. And so I sent him one.
My guys that have worked in the trailer absolutely love it.
That's brilliant.
So.
Yeah, I have 50 of them sitting in this box right here. Where is it? There it is. There's 50 of the main boards sitting in that box right there that need a little bit of rework. The one that you have does not have a noise problem, but the prototype that I have and the one that I just pulled out of there started having some oscillations on the bias generation circuit. I don't know why I wasn't having those problems before, but turns out op amps do not like to drive capacitive loads, and when you put 16 op amp inputs together in parallel, that's a lot of capacitance. And so when you have one op amp output trying to drive 16 op amp inputs, bad things happen. So I had to replace a 1 ohm resistor between the op amp output and all of the inputs. I have two 1 ohms just to mix. Anyway, I'm replacing a resistor with from a 1 ohm to a 10 ohm, and just increasing that to 10 ohms is enough to keep it from oscillating. So that's good.
Okay.
Jack says, I think the bias voltage for aviation headsets are 8 to 16 volts, as the ratio is at a different voltage from the intercom. The radio is at a different voltage from the intercom. Okay. So, yeah, I've seen as high as 36 on some aviation headset specification stuff. But I've also seen as low as 8. And so if they are designed to work as low as 8 but as high as 36, that gives me hope that 5 volts might actually be enough, because 5 volts is what you get when you're expecting to drive an electric. So
that tells me I need to look up the intercoms from the different airplanes I've flown, because the same headset works in multiple airplanes.
Yeah.
So if I find that voltage output for the microphone from the intercom, that should tell me what I need to drive my headset.
Well, that is one valid way of driving your headset. I think the point is, though, that the microphones work with such a wide range of voltages. The question is whether 5 volts is within that range. It'll never say that it works with 5 volts, because the range for aviation headsets, like I said, is from 8 to 36 or 8 to 16 or whatever.
I was thinking they were a 24-volt system. So, yeah, that's...
It's very wibbly-wobbly, timey-wimey, voltage, and, but 5 volts has never been in any of the ranges that I've seen. So I'm just really curious to know whether it'll work.
Okay.
So, and if it does, then maybe one of the things I do is, but getting those 068 sockets, the 3/16 inch sockets, those things are not commonly available, and they're not board mount, which means you're always wiring up, wires and panel mounting it.
Panel mount.
I just don't want to try and build that. I don't want to try and make a product for that. That is just such a pain in the ass. If there were other physical connectors, like I've seen a 5-pin XLR used pretty regularly as well. I would be willing to build a 5-pin XLR.
XLR is used in some of the commercial aviation stuff. I want to say Airbus uses a lot of XLR. But those are a different style of headset too.
Yeah. So I am not a pilot. I do not know how all of this stuff works. James keeps trying to make clear that the intercoms and the radios are different voltages, but intercom and radios are different. Intercom is 5 volts ish, and aircraft is 24 or 12 or 24 volts. Are you talking about power voltage, or are you talking about the bias voltage being sent down the microphone line toward the microphone?
Power voltage.
Yeah. We're talking about the bias voltage being sent down the line to the microphone. And that's the one that I've seen such a wide variable range. So, anyway.
Yep.
Cool. Yeah. Anything else you want to talk about, or any questions you have or anything?
No, that's it. I appreciate the help, and we will probably look at, putting that chip onto a circuit board and seeing what we can do. in the future.
Yeah, that sounds great.
That might be a product either you or I come up with.
4365. 4365. What are the chances that it's... Oh, sweet. KiCAD even has it.
KiCAD already has it for us.
23.8. DFN. One. Balls. Is that... How tiny is that? Very. All right. We'll go with that one. Yeah. Like it's right there, man. Okay, so what I'm going to do is I'm going to save this project and I will tar it up and I will send it to you, Steve. Okay. I'm going to say that you own this design. I am not interested in making this particular product, or at least not in the immediate future. I will, however, completely hand all of this data over to you, 100%, no strings attached. You own this now, and can do with it whatever you want without having to worry about royalties or any bullshit like that. You own this. This is yours. And if you do something awesome with this, I will absolutely talk about it and spread the word.
I appreciate it.
Cool. All right. With that, let's go ahead and wrap up. Steve, what is your preferred method of people to get a hold of you that you are willing to talk about publicly on the internet?
So I'm good on QRZ. My email's up there. Find me on pretty much any of the Discords, the Ham Radio Workbench, K5YVY, Clubhouse Discord, Toads, Ham Radio Crash Course. I'm pretty much on all of them. So, and I do have a small YouTube channel that I am trying to get better about making videos, and editing sucks. That's the problem.
That's why I live stream, man. No editing. Forget it. We're going live.
Well, see, the problem is when I'm doing projects like installing radios and stuff, the demonetization would happen very quickly if I was live.
Yeah.
Yeah, that would not be what I'd say. So,
well,
I work with sailors. What can I say?
Yep. Fair enough. Cool. Again, I'm Mark, N6MTS. I am also on the Ham Radio Workbench Discord. I'm on a bunch of other Discords as well, but I don't really frequent them. The only one that I read regularly is the Workbench, and then a couple of other social ones for other purposes. But hit me up on the Ham Radio Workbench Discord. You can get there by going to hamradioworkbench.com. There is a link to join the Discord on the webpage. That's not because we're trying to drive traffic to the webpage. That's just because reading Discord invite links is a pain in the ass. There are random characters in there, and I'm not going to read it out over the stream. So go to hamradioworkbench.com and click the Discord join link. I'm also good on QRZ. My email address is there. And if you are interested in any of the products that I sell, go to electronics.halibut.com, where you can pre-order the contesting console. And as soon as I'm done reworking some resistors on these things, I will be sending them out to folks who have purchased them. So thank you all so much for joining us this evening. Jack, just as a going away, a lot of people are saying great information. Thank you. Jack says, I need to get off my ass and finish building this HF antenna and get back on the air again. Jack, yes, you do. December 3rd. This is going to be the first time you hear the date. December 3rd, we are doing Herwaboda. Ham Radio Workbench on the air. Or we might just go with Workbenches on the air. We're going to be dropping a video on YouTube and a audio snippet thing into the podcast feed before too long. But it's looking like December 3rd from 10 a.m. to 2 p.m. Pacific time. So that's 1 p.m. to 5 p.m. Eastern time, U.S. We're going to be doing Workbenches on the air, where a bunch of us Workbench hosts, I think we've got everyone on board, including Jeremy. So we've got everyone coming, and we're going to be on the air. Various of us will be on different bands and different modes. Some will be operating portable and low power. Some of us will be working our home, high-powered station and whatnot. And then we are going to assign point values to us all. All of us are also going to be getting on to DMR Talk Group 31075, and All-Star 55915 at some point during those times. So even technicians who don't have HF can still work us and collect the whole set, and then we'll be sending out awards and whatnot on our 200th episode. So this is kind of a 200th episode lead-in celebration thing where we will be doing some fun stuff. So hamradioworkbench.com, and you can look at my stuff at electronics.halibut.com.
What I'm hearing is put everybody in your ham alert so you can find out when they're on the air.
Correct. We discussed briefly about getting a special event call sign, but I kind of like the idea of all of us using our individual call signs better. Because it's about working each of us, not about working at interchangeable ham radio workbench thing. Besides, some of us are in Canada, and so it would have to be 2 different special event call signs anyway. Excuse me. And that just felt weird. So I think, put all of our own individual call signs in there. Mike will be remote. That is entirely possible. It's kind of what he does. Awesome. Thank you so much for joining us, everybody. And say goodbye, Steve.
Goodbye, all. Thanks, Mark.
Be good humans. And click the end stream. And I'm going to wait for the waves because I think it will cut off the end of the stream. There's the wave. And then there's the second wave. Okay. Now I click end.